Okay.
So yeah, the paper I'm about to present, the name is Evaluating Superhuman Models with Consistency Checks. It's like a very recent model. It's under review right. It's like a very recent paper. It's under review right now. So just an introduction, like what exactly is are superhuman models, right? Uh, right now we have models which do tasks which humans can do, like machine translation and paraphrasing and stuff. But there are also models like AlphaGo and like forecasting models, which basically beat humans in human tasks, right? AlphaGo beat a world champion, and there are chess models which beat humans very easily. And all of these are like superhuman models. And in the future, like people are expecting a lot more AI to do a lot more superhuman tasks, right? So, like the problem with superhuman models is how do you evaluate them? That's like a very big issue, right? Because for machine translation, paraphrasing, and all of these, you know what the ground truth is. If it is presented to a human, he can tell whether this is a good paraphrase or not, whether this is a good machine translation or not, and he can basically label it. That is how evaluation is being done so far. But uh, but for superhuman tasks like let's say Go and chess, there's like hardly you cannot evaluate it the same way you evaluate for normal tasks like classification and all. Because the only way to evaluate, like let's say a chess game, is to play from the start till the end and then see if the model is winning or not. And let's say for forecasting, let's say I'm forecasting the weather for the next 2 years or something, and the only way to evaluate it is wait for the 2 years and then see if it's performing right or not. And this imposes too much risk, right? And it can't really be deployed in the real world if the evaluations are like that. So the paper proposes this solution to, it's not a full-fledged solution, but it's just one way of evaluating these models. Yeah, it's to evaluate the model's consistency instead of the end result. So when I say consistency, what it means is that uh, is it following some logical rules or not, and is it being consistent in its predictions? Uh, so let's say even in chess, there are some simple rules that even humans can like recognize if a model makes a mistake. And let's say think of like an autonomous driving agent, right? So if there is a stop sign, it has learned very well that if there's a stop sign, I have to stop. But what if for some reason there's no stop sign, but there's a traffic police standing there and he's just showing his hand to stop? The model might not stop, and this is like a very risky thing to be deployed in the real world. And yeah, so this is like the main picture of the paper, evaluating consistency, right? If you look at the left side picture, what is the answer to the ultimate question of life, the universe, and everything? The answer is 42. But if you ask if this is a prime number or not, it will say that it's a prime number, but 42 is not a prime number. This is logically inconsistent. We don't know if the answer is 42 or not, but what we know for sure is that 42 is not a prime number. So, and if you look at the right side, these are the three tasks they are evaluating on: chess positions, forecasting, and legal decisions. So for the chess part, if you look at the board, there are no pawns. So if you rotate the board, however you rotate the board, the game should go on in the same way. A model should give the same win prediction, however you rotate the board. If there are pawns, it's different, like because direction matters. But now it doesn't. So, and that is one way of consistency, because if you show it to a human, he will always just sit in the right direction and start playing again. But a model can't do that. Forecasting future events, let's say 100, okay, let's say the number of people who have climbed Mount Everest, right? In 2025, if it's X, and in 2030, we know for sure that it should be more than X, because the number of people who have climbed Mount Everest cannot decrease, it can only increase.
Mm-hmm.
So this kind of forecasting is, for humans, it's very easy to say that this is wrong. If you say that the number of people who climb Mount Everest today is 20, then tomorrow it should at least be more than 20.
Mm-hmm.
And this is like a consistency rule that should also be followed. These are just examples. And yeah, so what they do is they do it for three tasks: chess, forecasting, legal decisions. mathematically, if I were to put this a whole problem, if there are some inputs x1 to xn and they follow some kind of relation, in this case, let's say the chessboards are semantically similar. That's a relation, and the outputs should also satisfy relation. And like in the chessboard case only, if the inputs are semantically similar, the output should be the exact same probability. So they for the chess task they looked at Leela Chess Zero. This is like an open source neural network based chess model, and forecasting and for forecasting they use GPT 3.5 and GPT 4, and legal but for legal predictions. So I'll go into the details now. So for the first one, these are two examples. The position rotation thing I've already talked about. So if you look at the right one, that's a recommended move. So let's say there's there's a chessboard at this point of time, and I have a AI model predicting what should be done next. If I take the best right now, let's say my win probability is 68%, and if I take the best move that the AI model gives me, the win probability should not change, right? So that is also one consistency check they have. So I'll just go through the 4 consistency checks.
So there is one point. This is something coming very much in parallel, right? Is the following. This rotation, right? There is a concept in natural language processing called rotational embeddings, or you rotate the embedding somehow, right? So it's just very similar to positional encoding, and that was like you give the sentence embeddings and then you give the position of these words so that the model does not make a assumption of where the words are, right? And just randomly push that, right? So rather than randomly putting the words, the model look at the positional encodings that you have provided and make sure that the positional encodings are intact when it is learning.
Yeah.
Right? Now, then over the time when people talked about permutations and things of that nature, where they change the structure of the sentences or make some perturbations, the model is completely going off.
Yeah.
So what they come up with is that maybe a more better way of encoding can come is called rotational encoding. Right? By saying that you are trying to say that all the forms of rotations you bring in, right? So various permutations can come into the picture, and the model knows that what are the different ways a sentence can be constructed, right? So now assuming this, that rotate now if that method is true and that method is working fine, if I assume that, then this rotation position should also hold true.
Yeah.
Right? Yeah. But you're saying that it's not coming out true that way.
No, the way they trained the model is not that, right? They did not use rotational embeddings when they were training this model.
Yeah, so anyways, like even if you change the position, right, the model is in its very functional sense, it is still taking the embeddings, it's still taking the numerical representation of this chessboard.
Yes.
Right. At the end of the day, it's just the numbers.
Yeah, but the point here is that for in chess, in a normal game, the direction actually matters, right?
Okay.
But like if I am sitting here, the chessboard is like this, the direction does matter.
Mhm.
You can't rotate the board at any point and say that this is the embedding, it should be same.
Okay.
But what they do is they remove all the pawns.
Okay.
So whatever is left on that chessboard now is omnidirectional.
Okay.
So now you can rotate it, and whenever you rotate, the embedding should be same, is their argument.
Okay.
That is what they're testing it on.
Okay.
Like you gave it as a training example, they are using it as a testing.
So the model has not been trained on data which does not have fonts.
It has. It has, but it's just learning. It's just at the end. It's.
I mean, if you give a model training examples in which you don't have fonts like this, the model will eventually learn that the positions are same.
But that is the assumption. But it's not happening in real life, right? That is why it's not a safe model. I mean, not for the chess part at least.
Okay.
But like that is how the concept in reality is, right?
Yeah.
Models don't end up being how you want them to.
Right.
Actually, at this point, is there any doubt so far?
No. No.
Yeah. So like they look at 4 such things, forced moves. At some point, let's say if there's a checkmate, there's only one move I can make. Even at this point, the probability should not change. After I make the forced move and before I make the forced move, the probability should be same.
Right.
That is one. Both transformations is just the rotation thing. Position mirroring is changing all whites to blacks and blacks to whites,
Okay.
and then seeing the probability. It should be at the complement, right? And recommended move is just taking the strongest recommended move, and the probability of winning should not change. So these are the four things they are evaluating it on. They have like a data set of 400,000 board positions, and for the rotation part, they synthetically created 200,000 board positions. Yeah.
So once should we have different models or different application for every task?
In the sense,
I mean,
different models.
yeah, because we have, for example, we have chess, we have the prediction, forecasting, right? This is two different.
Yeah.
Should we have different tools and different prediction for this?
Yeah. So these rules I'm talking about, these are just for the chess experiments. For the forecasting part, they have different rules. I'll go through those also. That was your doubt, right? Yeah. So the results they found were like, so this is the difference in evaluation. What I mean by this is the probability change. So if the probability change of 0.75 is the 0.02%, it's very, very less. But there are minor inconsistencies. And if you go like till 0.05, the probability is changing for a decent amount of part. All it this experiment was just to prove that even in very rule-based game like chess, there can be inconsistencies. Like models don't follow human interpretable rules. They have their own rules which we can't interpret. And one more thing they did is brute force versus adversarial search. So in the rotation thing, right? They were synthetically creating data sets, right? In that, instead of just randomly creating data set chess positions without pawns, they try to use another model to like create pawns such that inconsistencies are created. And for this, the results have improved significantly. Like there are more inconsistencies found when they use adversarial search. So this was the chess experiment. This is like not from the safety aspect. It's just to show that even in such a rule-based game, there can be inconsistencies. This is how they started. And for forecasting now, this is like the more interesting part. So these are the consistencies they're looking at. First one, negation. So if I give a question and if I give an opposite question to that, I should get let's say if I give a question and a probability of an event happening, right? Now if I give a probability, if I ask for the probability of that event not happening, it should be the complement of it, 1 minus PA. So that is one consistency. The second one is paraphrasing. If I just paraphrase the event, uh, the probability should remain almost the same. Like it should be exactly the same, but paraphrasing should will involve some changes. So it should be almost the same at least. Monotonicity, that one, the Mount Everest example I gave. You need a monotonous, consistent answer for these kind of questions. And Bayes rule also they check in the same way. I was talking about negation, right? They just look at probability of events. So for this, they use GPT-4 and GPT 3.45 Turbo. They created their own set of forecasting questions for this. So like for the negation part they didn't create. There was already a data set for negation questions. Paraphrasing, they just created paraphrases of these questions using GPT-4. And for this monotonicity part, they manually created 50 questions, like this Mount Everest by year X, right? They just change the X year X to from 2025 to 2040 to see the graph how it goes. I'll show the graph. It'll be more understandable. So if you look at this result, right, this monotonicity result, woman 800-meter world record. So the prediction for 2025 was 1, and then it drops to -2 for some reason, and then 1 again, and then it keeps dropping. So this is like very inconsistent. What you ideally want is something like this: new medicines approved by FDA. This is like increasing because the new medicines cannot decrease in any case. But in most of the cases, you'll see inconsistent answers which don't make sense for humans at all.
Right.
So this is one of them. For negation, so this is like probability of negated and question, right? So the ideal graph is like this. but there are a lot of inconsistencies here and there. Same for paraphrasing. And these are like the actual numerical results. So if you see the probability change of 0.2 is the threshold they're taking. And for GPT 3.5 Turbo, more than 50% of the time, the probability is changing by 0.2 at least, like from expected.
So this 52.6% means that the 52.6% chance that the probability will change by 0.2.
No, from the example, yeah, kind of, yeah.
Okay.
From the examples, from the data set they have, the negation and normal pair, right? They want the probability to be the exact, like if the event A is occurring with 40% probability, then event A is not occurring should have a probability of 60%.
Okay.
And that's not happening.
Okay.
It's giving a 20% change. It's not showing 60%, instead it's showing either 80 or 20.
Okay.
Which is like very inconsistent. And like all of these percentages, right? They improve a lot with GPT-4 compared to GPT 3.5.
Okay.
So what they're trying to say is like this is a decent this could be like an intuition for a nice evaluation metric.
Okay.
Because obviously GPT-4 will perform better in terms of everything, right? Consistency also.
Right.
So that is what they're trying to show here. And yeah, this was like the forecasting results. I think these are like the main results for their experiments. The last one is legal decisions. So here they're only checking two things. One is paraphrasing. If I paraphrase the legal case document, what will the decision be? Will it change or not?
Okay.
And partial ordering is just I have a list of people who committed crimes. Now I have to predict bail predictions for them basically. Should I give them a bail or not?
I see.
Now what I do is I take the person's demographics, I change some part of it, like the number of crimes they committed, I keep increasing. Now I see if the bail prediction is increasing or decreasing. Sorry, is it showing? It's changing the decision basically.
Okay.
Like one experiment is making the profiles better in the sense like less crimes committed. One experiment is making the profiles less.
I see.
So yeah, the first task was human rights violations. So what they did was they took a huge list of human rights from European code. This is like a data set, and legal but is also a part of it is trained from it. I think I don't know, but yeah. So this experiment was given a legal case. Is it following the European court rules or not? That is the legal words classification task.
I see.
This is first experiment, and the second experiment is bail decisions. The one I explained just now. They use GPT 3.54 for that. So the results for that. So if you look at this, the bail prediction thing, right? If the number of crimes the person has committed before has increased, it's giving a bail, which is like very inconsistent. It does not make sense to a human being at all, right? If I committed more crimes, I should not be given a bail.
Yes.
But changing its decision from no bail to bail if I'm committing more crimes.
Agreed. Agreed.
For the same person. And for this black box, white box thing, I'll explain. So in that case, right, in the whole given legal case, there are a lot of statements. And what they do is they randomly paraphrase a part of it, and then they ask for the legal decision again. And the white box attack was they look at the model's final layer attention to see which part is it paying the most attention to, which part is it considering the most to give the answer, and they paraphrase this part.
Okay.
So in the black box attack part, you will see that there are hardly any violations. Because when I say violation, like the probability should be the exact same, but they are flipping at 50% part. Like this shows that the model is very consistent.
Okay.
But when in the white box attack part, the model is super inconsistent. More than 50% of the times it's changing its decision when you paraphrase a critical part of the case.
Okay. So, what does this black box and white box test means?
Okay, so like I have a whole document of the legal case.
Okay.
Now in this whole document, I randomly paraphrase a part of the document.
Okay.
I keep paraphrasing until my model changes decision or something.
Okay.
Like, and what you expect is even after paraphrasing, the model should not change the decision. So that is what is happening in the first case. The model is not changing the probabilities a lot, even though I paraphrase random parts. But the second, the white box attack, they take the whole document, they run it through BERT, right? They look at the final layer attention. So, and then they find the phrase that is paying the most attention to.
Okay.
Like there's a certain phrase saying this guy committed the crime before. If it pays the most attention to that, you paraphrase it.
Okay.
And now you see the decision again.
Oh, okay. Okay.
Now
So the left one is more random,
Yes.
paraphrasing, and the white box is more targeted.
yes,
Paraphrasing.
it is. Yeah, it's adversarial search.
I see.
So
I see.
more than 50% of the time, the model is changing its decisions. But just paraphrasing should not change decisions, right? So it's
Yes.
very inconsistent. And this is GPT-4.
Right. Right.
So
I
they
think, Ali, this is something you have, something that is relevant to your work.
But I didn't get the point that, you know, what is this red and blue?
Okay. So if you look at the like the x-axis, probability of violation of original case. The model's task is to predict if a right has been violated or not. So the bottom part is the ground truth. If the probability of given this is it violating or not, and the y-axis is violation in paraphrased case. So after I paraphrase, what is the probability of it being violated or not? So if you look at this red part, right, this means that uh, in the original case, the probability is less than 0.5, which means it's not violating the case. But in the paraphrased case, the probability is more than 0.5. So the model's decision has changed after you paraphrased it. Does it make sense? Yeah. So if you put the threshold as 0.5, these are all the cases which have flipped, basically, which have changed decisions. But yeah, is there any other doubts so far? Also for the build decisions part, model is mostly consistent, but the example I gave, 5% of the violations happen in this manner.
I see.
That was mostly it. That was it for the 3 small simple experiments they made.
I see.
And they created a benchmark data set also for the forecasting part.
Can you consider that the paraphrase impact every noise thing?
We could. So that is also something they have considered. So that's why they went through the whole data set manually also. And if you look at